In this video, we're going to talk about dimensional analysis, which is a tool that you'll use sometimes in order to either verify the units on a particular physical quantity in an equation, or maybe verify the units in your answer, or you can use this tool in order to figure out the units of an unknown physical quantity using the relationships that you know between the other physical quantities in an equation. So it's a tool in order to figure stuff out about units or to verify to make sure that the units were done correctly according to a particular relationship or equation. So it's a very useful tool. You'll use it a lot in physics. You'll even use it in chemistry and maybe even in biology. So let's talk a little bit when I say the words physical quantity and units. Let's make sure that we all understand what I'm referring to. So a physical quantity is typically something that an object possesses. It's like a characteristic that an object possesses that can be measured. So if you take, for example, a soda bottle, it has some kind of mass. It has maybe a height, a width, a volume. The liquid inside of it has some kind of density. All of these are physical quantities. You can measure those things. When you're talking about those physical quantities within an equation, usually these physical quantities are given a symbol. So density is mass divided by volume. So density is usually given the little symbol rho, and it is equal to mass divided by volume. So that would be a relationship between those physical quantities. And to put that into an equation, you need to use symbols because you don't want to write mass and volume every single time. Now, every physical quantity has units. There are standard units according to the various unit systems that we have. So like the SI system is a system of units, and the standard SI units for, let's say, mass, that's the kilogram. But of course, you could measure mass in other units. You could just say gram. Plenty of other units for mass, time, seconds, but you could say minutes, years, decades. All of those are units for the physical quantity of time. There are standard SI units though. So the standard SI units are commonly used, especially like in physics courses and your science courses that you'll use in college. So kilograms, seconds, and meters, those are the fundamental SI units for mass, time, and distance. There's also one other fundamental unit. We're not going to really use it too often. You'll see it a lot in physics too. It's the physical quantity of electric charge. And it has a standard SI unit of coulombs. Every other unit for all the other types of physical quantities are derived from these fundamental SI units. So take, for example, velocity. Velocity is a physical quantity that you can measure. It has a symbol that's a V, and it is a vector, so it has a little vector sign on top of it. Velocity describes a rate of a change in a position divided by a change in time. And so the units of that would be units of distance divided by units of time. So in SI, that will be meters divided by seconds, or meters per second. That's an example of a derived unit. It's using those fundamental units, but it's operating on them. So it's meters divided by seconds. So that's the difference between a fundamental unit, kilograms, seconds, meters, and coulombs, versus a derived unit, for example, like meters per second. Force is another common derived unit that you'll use a lot. So the physical quantity is force. Capital F is the symbol with a little arrow on top of it because it's a vector. The units in the SI system are called newtons. A newton is a kilogram times a meter divided by a second squared. So that's a derived unit made up out of fundamental units. Okay, so try really hard not to confuse the symbol for a particular physical quantity with the abbreviation for the units of a different physical quantity. Notice that mass has a symbol of M, and the standard SI unit for distance is the meter, which is abbreviated again as just M. So it's very possible to get confused here, so make sure that you know if you're talking about the physical quantity itself versus the literal units of a physical quantity, because it is easy to get those confused. All right, so some things that you want to keep in mind when you are performing dimensional analysis is a few just mathematical principles. The first one that I want you to keep in mind is that the output of trig functions, such as sine, cosine, tangent, all of the other trig functions, and the exponential function, so e, that's called the exponential function. The output of these functions is a unitless quantity. So the output is just a number that has no units to it. Similarly, the input or the argument of all of these functions, of all of your trig functions and the exponential function, again, is a number that is unitless. So when you input something into sine, you're actually just putting in a number that has no units to it. So keep that in mind. Those two things are really important when you're dealing with trig and exponential functions. The other math principle you want to keep in mind is when you have an equation with multiple terms. A term is like a quantity that is being added to other quantities. So your term might have lots of symbols within it, but then it's being added to another term. And so all terms in an equation, in order to add two things together, they have to have the same units. So keep that in mind, that all the terms in an equation must have the same units. If you're adding things, they have to have the same units. Same thing with subtraction. And then also remember that in an equation, whatever happens on the left-hand side of your equation must also be true on the right-hand side of your equation. That's what an equal sign means. And so all the terms on the right-hand side of your equation must have the same units, also as all of the terms on the left-hand side of your equation. So kind of keep that all in mind. And by using these fundamental principles, then we can go through the process of unit or dimensional analysis in order to actually figure out the units of a quantity that we might not know. We can use a relationship and we can use these math principles to figure it all out. So let's do an example of that. There are some steps to do, and I'll try to model these steps here for you. So this is an example where we have an equation. We have been given an equation that relates a bunch of physical quantities. We also know the units of some of these physical quantities. So we know A, we know the little w, that's actually the Greek letter omega, and we know the units of t, that's time. So we have three physical quantities that we do know the units of, and we are asked to figure out the units of B and the units of D. So I'm going to start by figuring out the units of B. Notice that in this equation, B is inside of the sine function. So it is within the argument of the sine function. So I'm going to do those first. Anytime I see a physical quantity that is inside of a trig function or an exponential function, I'm going to focus on that one first. So the principle here, remember that the units of the argument within that sine function have to be unitless. So that means that the units of B times the units of t squared, those have to be equal to the number 1. The reason I put the number 1 there is because the number 1 represents a unitless quantity. It doesn't have seconds or meters or anything like that. It's literally the number 1. Okay, so whenever I'm representing something that's unitless, I plug in the number 1. So the units of B, whatever those are, times the units of t squared, according to this equation, we know that those two things multiplied together must give us a unitless quantity. So then the next thing I'm going to do is algebraically solve for the quantity that I'm looking for. So I'm trying to figure out the units of B, which means that I need to divide both sides of this equation by the units of t squared. Okay, so that takes them out of the left-hand side of the equation, has moved them over to the right-hand side. And so now I finally see that the units of B has to be equal to 1 divided by the units of t squared. And now what I'm going to do is I'm going to actually plug in what I know are the units of t squared. So I know that the units of t, that says that it's the units of time. So now this is just going to be, I'm going to literally plug in 1 over units of time squared. So you can literally write the phrase 1 over units of time squared, or You could plug in literal units of time. As long as you are consistent and you're using the same units of time anywhere you happen to see it within the equation, that's fine too. So you might write 1 over seconds squared. Both of these things they mean the same thing. They're equivalent to each other, so both of these are correct answers. So the units of B have to be equal 1 divided by units of time squared. So if I literally want to plug in a unit of time, I'm going to choose the second because that's the standard SI unit of time. And so now I know that the units of B must be 1 over units of time squared, or you could say 1 over seconds squared. Okay, so that's an example of figuring out the units of a physical quantity within the argument of a trig function or an exponential function. All right, now let's do the next step. We're trying to figure out the units of the physical quantity symbolized by D. So I'm going to go to the next page and I'm going to copy over this equation. All right, now let's use these principles in order to figure out the units of the physical quantity symbolized by D. So if we look at our equation again, notice that we have 3 terms. We have the A, that's a term all by itself. So that is a term. This D times omega times the sine of BT squared, that's a term. And E, that's also a term. So all 3 of these terms, all the terms on the left-hand side must have the same units as all the terms on the right-hand side. So we're going to use that, and we're just going to focus on any terms that we know the units of. We don't necessarily need to use all of them. So we were not given the units of E. So we probably don't want to use that right now because we don't even know what those units are. At least we weren't given to them. We could figure them out. Let's focus on that term A, and then the term that is D omega times the sine of BT squared. We know that the units of A have to be equal to the units of D times the units of omega times the units of sine BT squared. Okay, we're only looking at units. I can ignore the E, that term right there, because it's just giving me redundant information. It's also true that the units of A are equal to the units of E. So we weren't given those, so let's just use the terms that we do know the units of, or the one that we're trying to figure out. So let's go back to this, and let's start. I want to do one thing before we actually solve for the units of D. Notice how I wrote there the units of sine BT squared. Recall that trig functions and exponential functions, they give us unitless quantities. So the units of sine BT squared are unitless. There are no units. So if you want to, you can just plug in the number 1 if that helps you. There are no units. So there are some other quantities like pi, some other fundamental quantities out there that are just unitless. And so when we write there units of this thing, if it has no units, it goes away. You can just plug in the number 1 instead. Okay, so now let's go ahead and do some algebra and solve for the units of D, because those are the things that we're trying to figure out. So I'm going to divide both sides by omega, the units of omega. Okay, that gets rid of it on the right-hand side, brings it over to the left-hand side, and so now I know that the units of D are equal to the units of A divided by the units of omega. Now I can actually use the chart that was given to us. I know what the units of A are, and I know what the units of omega are. So let's plug in that stuff. That would be units of length divided by time squared. And all of that is divided by units of omega, which was 1 divided by time. Now I can simplify this. I see time is in 2 different places within this fraction. It's actually a compound fraction. So I want to rewrite this to help me figure out how to eliminate or to simplify the fraction. Remember that dividing by a fraction, instead of doing that, we can multiply by a reciprocal. So I'm going to rewrite this. I'm going to rewrite it as units of length divided by time squared. Instead of dividing by 1 over time, I'm going to multiply by time over 1. And that helps me to see that this time will cancel out with the exponent down there. And so overall, I get that the units of D must be units of length divided by time. So if you wanted to actually plug in literal units, you could say maybe meters per second. That would be the units of length divided by a unit of time. So either one of those two things, actually saying units of length divided by time, that's a perfectly fine answer, or actually giving me literal units, meters per second, that's also fine too. So here's an example of performing a unit or a dimensional analysis using the principle that the units of every single term must be the same, and that the units of a sine function, any other trig function or exponential function, it's going to return a unitless quantity. So notice how the units of sine disappeared. They were just really the number 1 because they were unitless. And that's how you do some dimensional analysis.